Welcome back to Codex. Our speaker today is Felix Krahmer, who is a professor in the Department of Mathematics at the Technical University of Munich. Professor Krahmer received his PhD from NYU in 2009 under the direction of Percy Dieft and Sinan Günther. He was a postdoc with Holger Rauhut at Bonn, and then a junior professor at Göttingen before joining the faculty at Munich. Felix is known for analyzing randomized sensing methods for various fundamental problems in signal and image processing. Today, he will tell us about blind deconvolution. Take it away, Felix.
Thank you. Yes, thanks a lot for the invitation. And I can also repeat what John just said. Feel free to interrupt if you don't mind being recorded. And if there's anything that requires further explanation, or Emily, if there's anything that you're missing because it's on the slide, feel free to ask. And I should mention what I'll be talking about is partly like work with Dominik Stöger from a couple years back, and now it's some very recent results that I included about ongoing work and some surprising findings with my current master's student who will soon move on to the PhD level, Julia. So let me start with the first talk. As I mentioned, this is with my PhD student Dominik, who is now a faculty or tenure-track professor at the KU Eichstätt-Ingolstadt. You may visit this place if you're going to attend ITCHA in the fall. So as the title suggested, the talk is about blind deconvolution. And I'm sure when you think about blind deconvolution, you think about something like this. So you have a camera that's taking pictures, but you are a little bit nervous and shaking, and that introduces a blur. So in the end, you don't just take the picture that you want to take, but also while your camera is shaking, a picture that is a little bit shifted. And in the end, you have a superposition of all these things here. So you can say, mathematically, you can formulate this in terms of a convolution. So you're having the little squares here, which correspond to the different shifts that are superposed. So while I was shaking, I was moving a little bit to the right and a little bit down and a little bit up. And then you are taking, like, averaging these shifts of the image is exactly the convolution here. And you can see this XL minus K is the shift. And then you're sort of having the weighted average of this. But one thing that we're doing for simplification here that is not, I think it may be actually indicated in the picture as well. So we are doing something that can be achieved by zero padding, by adding some zeros on the left and the right. So that makes things a little bit mathematically simpler, because the problem is that if you're adding all these shifts, they don't have all the same dimension. So what we're doing in order to fix this problem is whatever we're shifting out on the right, we're moving back in on the left. And so that is just by including like zeros, increasing the size of the image by a factor of 2, that sort of is not much of a restriction. Okay, that's the convolution. And now the title says blind deconvolution, because of course, if I'm taking this picture here, then what I would like to have is this. So we're having this convolution of our filter and our image, and we would like to get just the image back. And this is what you may have in mind, but what we are having as our main motivation is a related problem with a very similar mathematical formulation, but it's still slightly different. And that's mainly resulting from applications in wireless communications. The task here is that you have a message that you want to deliver via an unknown channel. And I can already tell you beforehand that what I will propose to do is to introduce redundancy before the transmission, so that maybe we have a hope recovering the signal. What does this mean? So we're taking our signal M and we're using a linear encoding. So that's my justification of giving this talk here in this seminar. We're doing a linear encoding and getting a longer vector that we're then transmitting, and hoping that this redundancy that we have created will eventually help us recover the signal. So now we have to see what's happening with the signal. We want a convolution. So in the end, we have like convolution of, again, some W and some X. But here we're having the W represents the channel. So what we're having is the message is going directly from the sender to the receiver, but at the same time, it's also going to these buildings, and it's reflected in the end. We're again having a superposition of different copies of this, but here we can say, okay, if it's reflected here and here and here and here and here, then maybe the intensity is very, very small. So what we can assume is that only the most direct paths are it. And so if you're thinking about this matrix B, that would then correspond to a few columns of the identity matrix, because sort of you're having an embedding, like just think of the identity matrices that correspond to how much the signal is delayed, then only the first few are actually significant, and everything after that is maybe not. So that's why we're having some, like one example would be this matrix of columns of the identity, but it's not the only example. And then things are the same. We are having a received signal that is the convolution of the one signal and the other signal, but then of course potentially added some noise, could be corresponding to the paths that I left out, but also external noise of various sorts. And so now again, the goal is to recover the signal, but the most important things, we want this message, right? We have we encoded it into this higher dimensional space, but what we're interested in is n. Any questions regarding this problem and the relation between what I talked? If not, let's move on and go. So I could also say go back 10 years in the literature, because this is something that was observed in phase retrieval and by many people, including I think Radu, who was in the audience, as I saw, was one of the first people who studied this problem and proposed to look at bilinear or quadratic functionals via some sort of lifting, in the sense that we're noticing if this obturation here is bilinear in these inputs H and M, then that is nothing else than saying that it's linear in the outer product. So there's the unique linear map, such that this convolution can be written as the linear map applied to H times M star or M transposed. It depends a little bit how you exactly normalize this. Okay, so that is an observation, as I said, for phase retrieval, was proposed by Radu, and then later on, I think going from quadratic to bilinear is not such a big step. And why was this proposed? Because like you can now try to solve this linear problem using the linear methods, and then later on, people incorporated also the fact that this object that we're having here is our argument X, has an additional property that it is of low rank. So that's why in this case of rank 1, so we can say that finding X is a low rank matrix recovery problem. Okay, so now we want to find X, and we could say if this vector E here, this noise vector, has a norm of size eta, one could try to solve this problem. Argument of the rank subject to this constraint ax minus y in the true norm being less or equal to eta. But I think this is something that has been discussed in various contexts, that such direct combinatorial formulations of the problems are typically NP hard in general. So what one can instead look at under certain additional assumptions on B and C is that you can consider a semi-definite relaxation. So instead of trying to minimize the rank, you're taking the same constraint and then you are minimizing the so-called nuclear norm. And the nuclear norm is the sum of all the singular values. Some of you may remember this type of intuition of relaxation from works in compressive sensing, where you have sparse signals and then you get the L1 norm. And here you can think of this as really being analogous, because if a matrix has low rank, you can think of that the vector that comprises of all the singular values is sparse. And so this is exactly just the L1 norm of this very vector of the singular values. Okay, so this is what has been proposed by Ahmed, Recht, and Romberg. And now, of course, we have only stated things in general terms. And I have to say, I already said we need to make some certain additional assumptions. And the assumptions that have been proposed here is, first of all, this form here, BH convolution CM plus noise. Then they have the model that they are working with, that we will also be discussing here, is what nowadays is sometimes called adversarial noise, in the sense that we don't assume that E is following a certain random distribution. We just assume that its magnitude is bounded by some value of eta. And then the additional assumptions are that we introduce some type of randomness. As John already mentioned, this is a central object of study for my research. In this case here, assuming that this matrix here has standard Gaussian entries. This is not so much of a restriction because recall that this matrix C is our choice. We are taking our message and we are encoding it before sending, so we can more or less do a lot of things that we would like to do. Of course, some things like binary matrices, fast transforms, something could be additional constraints that one would like to consider. But still here, it's not the thing that say, is this completely useless because Gaussian will never happen in practice? In this case here, it's not happening because we are doing it. So there we can at least do something along these lines. But for B, we don't have this freedom, because this, as I mentioned, is from the channel. This could, for example, be corresponding to the first few columns of the identity matrix, or you can have a more general formulation. In this case, what we're assuming is sort of some assumptions that are inspired by this model of having the first few columns of the identity matrix. Namely, we're assuming that they form a tight frame here. B star B is the identity. And we're talking about the Fourier transform, that this has rows of equal norm, which is also the case, because if you're taking the Fourier transform of the first few rows of the identity, you're getting the first few columns of the identity, you're getting the first few columns of the DFT matrix, and that, of course, obviously has rows of equal norm. The reason why this is a natural or a useful assumption here, it's natural to think about it. If you, in order to see that, let me just write something here. What we know is that like an important thing that's driving here, the intuition is that if Y is BH convolution CM, let me just omit the noise for the, or like plus E, and then the Fourier transform is the Fourier transform of BH Hadamard product. It's like entry-wise product of the Fourier transform of CM plus the Fourier transform of E. So basically, that's why we're having these Hadamard products. And if one of these values is very, like here, an entry-wise project, so if an entry of this vector is very, very small, it means we're taking the product of something that includes some information that we would like to have with something very, very small, so information gets lost. And that is what can cause a problem. So in some sense, this type of condition, and we will see more conditions that are related later, are actually have the intuition behind them is to ensure that this doesn't happen, that not because this B here is unevenly spread, that's why some certain information will potentially get lost. So this is sort of some general information that this B is sort of well distributed. We will do something addition of this vector H that sort of ensures that the joint thing has exploded. So, but let's this last thing that I said is related to this coherence parameter, which will come in a second. But let's assume that there is some coherence parameter here, mu H, and then what they show is that assuming that the number of measurements L, I mean, here it's a little bit tricky because the convolution doesn't have measurements in the sort of form that can be freely chosen, but the measurements here is like sort of the embedding dimension of B and C, because if you're taking the circular convolution of two vectors, the length will remain the same. So that's why we have to sort of think about how as much as the redundancy in B and in C, and that is sort of encaptured by the ratio between L and K or L and N respectively. And so that's what we have here. And so we said that this sort of this embedding dimension that we're having, that's large, is supposed to, it's enough if it's up to this coherence factor and some logarithmic factors, it scales linear in these two dimensions K and N, which is great. And then if you look at this reconstruction condition, what they show is also very nice, because if you think of, let's say, eta is 0, we have no noise, then the right hand side is 0, and we get exact recovery of our matrix via this method. And as I said, so let's talk a little bit more about the coherence. Okay, parameter on the next slide. But before that, okay, I was too fast here. This is already what I just said, that if eta is 0, we have exact recovery with a near optimal number of measurements. And now, because now it's getting interesting, we talk about the coherence parameter later, because I skipped something. Like this, you can see in orange, there's this factor of square root of K plus N. So for some reason, we have the noise level that we add to our signal, but in this proof here, or in this result, the noise in the reconstruction is amplified by a dimensional factor. This you can think, of course, you have to carefully think of what's the right scaling, but I can tell you this: we've chosen the scaling here in such a way that this factor should not appear, in the sense that if you don't do the structured convolution measurements, but say Gaussian, then it doesn't appear. And also, if you just run experiments, then you don't see this factor. So that was sort of the starting point that we had, and say, like, it's very strange that we find this dimensional factor here. And let's see, I mean, we head out in some sense to say, okay, let's try to devise some new proof techniques, better proof techniques, that we don't get this spurious dimensional effect. But before we go into more details on that, let me talk a little bit about what this coherence term is like. It's actually the maximum of two coherences, mu1 and mu2. And this one, the first one, mu1, is very much related to the intuition that I had before. Previously we said that FB should have rows of equal size, and then also when I now apply this vector H to it, then this thing should still be relatively evenly spread, so that infinity norm should not be too large. The mass shouldn't be concentrated in a restricted number of entries, because that's what I mentioned coming back here again. If mass is concentrated in only few entries, it's more likely to get lost in the pointwise multiplication. And yeah, the range can be in 1, it's optimal, then we would get this near optimal bounds. But if we have bad luck and we get in the worst case we get something like K over square root of L, and then things are subtle. So that's why. But this is not a proof artifact, at least it's suggested also by experiments that Ahmed and others did in their paper, that if mu1 is large, indeed more measurements are needed. And that is different from mu2, and so that's why I also won't spend too much time on it. Some technical term that was already suggested in the paper that it's a hope that it's a proof artifact, not necessary that their proof somehow required. Okay. I knew I wanted to I think I decided to not. I don't think I will make the matrix completion again at the end. But the main point is that what I already said is that we could now compare things that are happening. So if we want to look at this noise robustness problem with this dependence, the potential dimension dependence on eta, as I mentioned, you don't have this in Gaussian measurement matrices, which have the restricted isometry property. Things behave very nicely. You also don't have it in phase retrieval, when you say you have Gaussian measurements. Also, you have a scaling in the noise level that is linear. But for blind deconvolution and matrix completion, this was completely unclear, because in both the proofs that were available, in all the proofs that were available for these two scenarios, you had these factors. And then there's more robust PCA and more problems that one could potentially study. So, and to summarize, is like, despite the popularity of convex relaxation for low-rank matrix recovery in the literature, their noise robustness is not well understood. And so what is the problem? I say, I'm talking from the perspective that we had when we started working on this problem. So one, I think a number of people were thinking or believed that part of the problem was the proof, because the proof is based on the so-called golfing scheme that was originally developed by David Gross, and that's building on the existence of an approximate dual certificate with high probability. And sort of the understanding that we were hoping to follow was that it works very well in the noiseless case, where this X naught that you're getting is expected to, or the true solution is expected to be the minimizer. So having things that are pointy at these polytopes, and those things can directly apply. But in noisy problems, maybe because we're wiggling a little bit, we don't have these very nice properties of the true solution anymore. So we don't really know the actual minimizer. So this was what we were thinking. And that's why we thought, okay, maybe we want to look at different or alternative proof methods to this golfing scheme. So recall now, so what are we doing here? So let me just recall to not lose anyone. Let me recall we have some vector of length k and a vector of length n. We both embed them into an L-dimensional space, and then we're taking the convolution. We assume that L is much less than k times n, because otherwise there's no need to do these nonlinear methods, because we can try to work something that's inspired, or it's very at least close to the dimensions where you can solve a linear problem. So if we are in the scenario, we are trying to solve our problem by nuclear norm minimization subject to this constraint about the noise. The noise being bounded by beta. This is what we are working towards showing. And it ended up happening that we were very surprised, because our complete intuition that we had when we started working on the problem proved out to be incorrect. Because what we could show is, like, we could say, let's see what would we need if things are incorrect, right? If the true solution, like, what would an alternative solution need to satisfy if it's supposed to be some type of a counterexample of the result that we are developing. So first of all, the alternative solution must be feasible, right? If we're having noise below eta, then the measurements arising from this alternative solution must be close to the true, must be in a distance to the true measurements, or to the observed measurements of at most times, because otherwise, if it's not feasible, our minimization problem is not able to find it. At the same time, this vector x, I mean, it would also not be a problem if it had a larger nuclear norm than the truth. So we need to ensure that this alternative solution needs to have a smaller nuclear norm than hm star, which is the true solution. And that, again, that wouldn't be a big problem, because if, like, it could be that we're having a true solution and we're wiggling a little bit, and then we're having a different solution. But as long as things are close to the true solution, it's not a problem. And now we have to think of what kind of closeness we would expect. Going back to the other result that we had here. So what we are looking for is a closeness that sort of scales with our noise level eta. Then we had this factor square root of k plus n. So here we're having that it's less or equal to, we would like to have a constant times eta. So if we want to disprove this, our counterexample must satisfy the same condition in the other direction to be a counterexample, and with some additional dimensional factor k n o n t. In this case, what we get is k n over l. Well, this looks different. We had k plus square root of k plus n, and now we have square root of k n over l. So is this really a counterexample? So let's to see that this it is. Let's assume that the two dimensions k and n are the same, and we are also in the competitive regime where things are scaling linearly up to logarithmic factors. So here, this number L that of measurements is near linear. So what will happen? Up to log factors, the following. So what we said was given by the previous result is tau times the square root of k n over L. And now we're just plugging in this here. Basically, this L would cancel the k, then the n remains, and n and k are of the same order. So what we get is k plus n. So we get exactly, in this competitive scenario, we get exactly something on the order of what we had in the result. So the factor of square root of k plus n is not a pure proof outcome. On the other hand, it's that's why I said some sort of a counterexample, but it's not quite a counterexample. And let me just tell you with a picture how I mean this. So what basically we have shown is, here's the true solution. So here's the true solution. And now we have established here, say, the alternative solution. This is x and x tilde. And say the alternative solution has a nuclear norm that is smaller than x or equal to x, but at the same time, it's sort of far away. And has measurements that are similar, but it's sort of far away. Because we are sort of moving along the space of measurements. Right. But that doesn't mean that this x tilde is necessary. It has a smaller nuclear norm, but it doesn't mean that it's the minimizer, because what's actually true in this picture here, if you look at it, there is another x tilde tilde that has an even smaller nuclear norm and is again close to our true solution. So this is something we don't know if this happened. We actually suggest this may be the case, that it's that the true minimizer is not such a counterexample, But even if it is, then of course we have to be very careful, because it means that there's a lot of instability in this point. Because if there's so many good and bad solutions close by to each other, then this could potentially be a problem. So let's think about the analysis a little bit. How this was established. The idea is the following. So we have it follows the general idea of the convex geometry of linear inverse problems that was suggested. It was in a very influential paper some years ago, of analyzing descent cones. So you're looking at all the points that are the cone of all the points that have a smaller nuclear norm as compared to this x naught. And then you're asking, first of all, if you're just looking for the solution with equality constraints, you ask, is x naught, this is so basically this subspace here would be the set of points that give rise to the same measurements. And among all these potential solutions, only one intersects this nuclear norm. And now this is true for the equality constraint. If you are operating with noise, you have to have a little tube around the space, because you don't need to match the measurements exactly, but only something close by. And then the question becomes, how much does this tube intersect this descent cone of directions in which the nuclear norm decreases? And this is captured by the so-called minimum conic singular value, which is defined like this. So you're looking at the on all the different descent directions, so the directions in which the nuclear norm decreases, and then you're asking, so what happens to the measurements? How does the measurements scale in these directions, or change potentially in these directions? And you say you divide it by the displacement that you're going in this directions. And then, as I mentioned, in a noiseless scenario, you just need this thing to be greater or equal to 0. That is, means there's a unique solution. And by just comparing this size of the tube to this intersection, you can get a guarantee that says the reconstruction error here, in this case, in the Frobenius norm, is really scaling. It's the noise level. We want something that's bounded times the constant times its noise level divided by the minimum singular value. And for Gaussian matrices, this is in fact a well-known observation or well-known fact that the minimum singular value really scales like a constant in this normalization of frequency. So one potential difficulty that we have in contrast to Gaussian measurements here, because of the convolution, is that we don't even have something that's independent of our base point x naught. If we have coherence inputs, we already know that if this coherence constraint is violated, things will behave badly. So if I take my descent point and move it to a coherent anchor point, I will have a rather bad behavior. And if I move it to an incoherent point, it should be a better behavior. So that's already a difficulty why the exact proof techniques don't work out. And indeed, what we show is that in this case here in this context, we really have a counterexample in the sense that showing that this minimum conic singular value that's used in these proofs is indeed that small that you can bound them by this dimensional constant inverse. So basically, we said the other thing is that we said a large constant is now a very small constant. So it doesn't behave like the Gaussian. Then you can use this to prove the previous theorem. But yeah, okay, this sounds very negative, which basically says that all hope may be lost. We have just shown that blind deconvolution is unstable. You get bad dimensional factors and so on. But that's not quite the case, because for this is true only for very, very small noise level. So I will have a similar result in a different, slightly different context later. So let me just very briefly mention what this exactly says. That says basically you should think of alpha to be the threshold. So here we have the max of tau and alpha. So if we are for very small noise levels tau, things just behave like a constant alpha here. So that basically things don't decrease anymore. But as soon as you are above this threshold alpha, then this tau factor here dominates. So you have something that really scales linearly in tau up to this logarithmic factor. So no, like it's still a dimensional dependence, but a much weaker dimensional dependence than before. So for high noise level, we have a near optimal recovery. So the picture that you should have in mind is this here, because I mean, I deliberately showed you pictures that were inspired by corporate sensing and L1 balls, and I think many of you have seen them, because I didn't want to sort of I want to sort of illustrate how we were thinking about this problem. But as it turns out, it looks much more like this. So the descent cone with the nuclear norm is more like a cylinder. And apparently here, because of the structure that we're having, we are like locally a cylinder that has some very nice points in highest dimension and some not so nice points. And apparently what happens due to this convolutional structure, we're entering at a not so nice point. So where the descent set is not very pointy, even though the underlying object is of low rank. So what we should think of is more like a smoother type object, like we have here. And then you can see that even if it's close to smooth, you can draw the descent cone. It's very, very wide, because you have to sort of use these tangential parts, and that makes the cone very wide, even though there's curvature. The descent set, which I noted in red, is actually much smaller. On the other hand, if I now say I want a good explanation only outside of this orange strip here, then I don't need to make sure that inside the strip things are included. And so that's why I can take the green cone, and the green cone includes everything of the descent set that's outside of the orange strip. And this is the intuition of this partition here. So we are splitting up our vectors into the near orthogonal parts and the complement of them, and analyzing them separately. So when we are in this curved, when we're in this part of the near orthogonal elements, then we have to use the fact that the nuclear norm is curved. And then we can use Mendelssohn's small ball method. Basically, we can say we can only go a small step. There may be bad directions we can go, but we can't go too far, because otherwise, if we're thinking here, we could go tangentially, but then just because it's curved, it will be very soon, like we could go a tiny little bit, but then it's curving down, and we will be leaving the descent set. So we can only go a small step. And on the other hand, this other part here you're using for this sort of well-behaved part, then you can use the Mendelssohn small. Okay, so this is a brief overview of this. Now let me say, okay, this is sort of the status that was 3 years ago, and we have been with my current student Julia, as I mentioned here, who's a master's student, still in joint work with Dominic. We have been sort of continuing the problem, trying to understand things a little bit better. Because what we want to look at, or what we have been looking at, is what happens in the intermediate range. So let me recall where we stand. So if you if you got lost in some of the details on the previous slides, this is maybe a good point to jump back in. So what we are looking at here is we're looking at the case of arbitrary noise vectors, so adversarial as we want, but we don't make any additional assumption about the distribution. What we said, if we don't know anything about them, we can only say that up to logarithmic factors, we get a scaling of the noise level times some square root of k plus n the dimensional factors. If we are above a certain threshold alpha, and then at the cost of increasing the number of measurements by a constant that depends on this threshold alpha, we can get better, we can get a linear scaling in terms of embed and have a much nicer dimensional factor in the sense that it's only logarithmic. So this is where we stand. So now, of course, this is a good step because it shows us that there's hope, but it may not be satisfactory because there's an intermediate range. So it could be if the noise level is it could be that the noise level is too large for the first bound to be meaningful. It could just be that you have something that's scaled badly in dimension, and then you basically can't say anything about the reconstruction quality, but yet at the same time not as too small for the second bound to apply. So that's why we require the alpha, and so that's why there's some intermediate regime. In particular, for if we think of E to be a small constant, then also the second bound is meaningless, right? So we have now improved the dimension.
We have Ghostwriter here.
It's not just me. I'm guessing his internet dropped off.
No, his laptop is restarting.
I just read it. Thanks, Joe.
Hence Joey's giggle. Yeah.
Yeah. I'd pause the recording so that it's easier to edit this out, but I don't have to edit it out.
I mean, I'm not going to edit it out either. So
It's Dustin's responsibility. So does anybody have any good jokes? Dustin?
It's a long reboot.
I think he's back.
Hello, sorry about that.
No problem. Carry on.
I will be returning, and I hope, yes, thanks for waiting for me. Yes, I hope you got my little message here that there's nothing I could do until the laptop was back. So yes, so what we were now want to look at is what happens. We want an error bound that is, so let me recall where we were having some bounds, and if we have some small constant as our noise level, then the first bound would give you a dimensional factor that scales like square root of the dimension, and the second would give you a noise level that scales like logarithmic factor that the dimension, but still that's both of them are not very interesting if you have a small constant, because then they grow with the dimensions. So we would like some error bounds that are less restrictive and yet more precise. That sounds sort of attacking the things from two angles, but in fact, here's what we found. And the constraint here is very similar to what we've seen before. Some coherence parameters are entering the game, and we have basically something that's linear in K and N. And now, like, we're having some noise added, potentially adversarial noise added with the 2 norm less or equal to eta. And then what we found now using our newest results is that this reconstruction error has 2 terms. There is a linear term, like now truly linear, scaling like 4 times the noise level. And then there's this other term that is like the square root of the noise level. So so let's see if this is natural. So if the noise scales linear, like sort of if you're looking at a proportion of tau, say a relative error of tau, then indeed things work out exactly. You have 3 times square root of tau and 4 times tau. So it has the right scaling, and it bridges the result for small and noise, small and large noise level. So in some sense, if we go back, so there's no spurious logarithmic factors, it's also meaningful for small constant noise level. So if we go back to this picture here that we had, then maybe one way to think about this is that if we are approximating the descent cone, if we observe approximating the descent set by a cone, then of course the size of the cone will grow linearly the further you go away. So that's the traditional way of looking. But so what we have been, what's sort of the next step after sort of this division that we're having here is to say maybe we approximating this descent set by a parabolic structure, which basically means that close to the tangential point, we having this parabolic scaling or like quadratic scaling kicking in, so we're getting only a dependence of square root of tau. And if you're further away, then of course you can see the cone, and then things are becoming linear. So in that sense, this really gives us an understanding of what's going on, because this is a bound that is really tells us how things are going to zero and what speed, and it's not contradicting to these previous results that had these dimensional factors, because you can think of, we never said how small the noise level would need to be. So that would basically mean that if this noise level is as small as 1 over the dimensional factor, then or 1 over the square of the dimensional factor, then of course like you can think of this to be a tau times this dimensional factor that we're having. So that's how you can see that how these things are not in contradiction to each other, and which also says that these dimensional factors may be necessary, but they are only relevant in very unrealistic scenarios where the noise level is extremely small, and I think that's not typically what one is encountering. And if the noise level is extremely small, then maybe like if it's an inverse dimensional constant, then losing a dimensional factor is maybe not bad. So there's a few open questions. First of all, what can we say about the actual minimizer in the scenario of small noise? So we said we had some results on this, but like previously, the question is, do we have linear? Like we only had sort of an alternative solution that doesn't necessarily need to be the minimizer. We can still ask the question: is the true minimizer close to the true solution or not? Coming back to this picture here. Yes, all these points that are in this parabola are maybe of smaller nuclear norm than x naught, but if you're having a certain constraint, maybe you will not land on the boundary here, because there's always a point in the middle that's even better. We don't know that. And then what happens for rank higher than 1? In this case here, we had only blind deconvolution, but you can have a higher rank in, for example, blind demixing and deconvolution, so that you don't have just one rank 1 component, but you have a superposition of a multiple of them that would show up in this wireless communication application when there's multiple users that are all communicating at the same time, and you would like to recover all the messages. And sort of it's not so clear what happens in this case, because you also get spurious dimensional factors there. And the other point where the negative results that I've been showing you in the beginning would carry over is the problem of matrix completion, where of a low rank matrix only very few entries are observed. And so that's actually work in progress that we're trying to see to which extent we can also generalize these positive results that we saw at the very end to the matrix completion. So I think that's the end. I would like to thank you for your attention. And I just wonder, before I welcome any questions, I would like to say that I'm looking for talented students who would like to pursue a PhD or a postdoc under my supervision. So if you know anyone who's on the job market and would be considering to move to Germany, please let me know, and could potentially be interested in things like this, but maybe with connecting it more to problems in machine learning, then please let them know to just send me an email, and or you can also send me names if you want to recommend anyone, and I can contact them directly. So that after this shameless advertising, let me, of course, thank you again for your attention and ask if there's any questions.
All right, thank you. First, before questions, everybody smash the reaction button. Thank Felix for the great talk. And with that, anyone is free to chime in.